Hi everyone. So our last lesson we did volume that was rotated around an axis right here. Calculus can not only be used to find volume of solids created by revolving, and when we did that we used pi r squared minus pi r little squared, that's the outside minus the inside. So we can go around the axis, but there's a different way to get a volume, and this is called a cross section that are geometric shapes. So we're going to be looking at 4 different geometric shapes. You will derive the formulas. We'll do the formulas for these 4 shapes. Okay, so it's kind of cool. Do you see how the shapes are popping up from the paper? Now, do you want to spend a couple hours making these? No? Can we just pretend we did? What do you say? Watch and... Okay, I'm going to show you a video because it's different than the revolving. Let's see if I can do this. So this is YouTube within YouTube, okay? Sorry, I can't. There we go. Maybe, I don't know. Okay, let's, oh my gosh, technology. There we go, yay! Okay, I put it on super slow-mo. So do you see how the squares are growing? And, how do I go? Oh, sweet, okay. So between the 2 curves, which aren't drawn on this animation, between the 2 curves is a line. So if it makes the shape of a square, the height of the square will be equal to this line here. Okay, but what's this line? This length here would be a function, say f, minus the function g. So it's top minus bottom is the length of this line. So to find a square, it would be the same length going up as going down. So do you agree how it's not revolving around anything? They're popping up from the page to make this shape. And this is a square. We're going to do half circles and triangles. Pretty neat, huh? So there's your 3-dimensional finding volumes of constant. Justin Timberlake, Disney piano. Back to the examples. Here we go. Okay, so this is like an official page of notes with formulas, and then we'll get to the examples in class. So if we have a cross section that are squares, then our little picture here, what color am I using? I was going to use green. So in this little picture here, you see how this is a graph of F and C, and then this is G. Oops, sorry guys. Okay, so the length here is F minus G. It's just turned, it'd be like that, F minus G. So then the area of one square, so this is the big idea. What would be the area of one of the shapes? So find the area of the square above in terms of F and G. So write it out. Area would equal F of X minus the G of X times itself, right? So that's going to be squared. You agree that an area of a square would be like side squared? Okay. So if that's, oh, shoot. Sorry, it froze. I'm back. Okay, the area of one square is top minus bottom squared. Do you agree that's the area of one square popping up out of the page? Okay, what happens if we take a square and add it to another square and add it to another square, and we add, man, this is the worst example. And we add up all these squares. If we add them all up, we get a bunch of volumes. You agree? So that's what we're going to do. If all, gosh, that's what I just said. If all the cross-sectional areas were added up, the total would be the volume of the solid pictured. How do we write this in calculus using an integral? The total volume would be, we're going to go from A to B, of the f function, or the top, minus the bottom, squared dx. That's it, y'all. Is there any pi? How come there is no pi? Are we making pi r squared? The pi came from pi r squared, which were circles. Do we have any circles here? No. And why are we doing top minus bottom squared? Only because this shape is a square. It's going to change for every shape. Almost easier than the revolving because there's no axes. We don't have to worry about axes. Okay, so let's look at this. These are neat. These are isosceles right triangles, which means, what do you notice about this and this? this and this. This area is what? This area is half that area, right? So our base here would be f minus g, top minus bottom, and then the height of each triangle would be f minus g, f minus g, f minus g. So you can see itty-bitty triangles where the lengths are itty-bitty here, and then the triangles get really big the further apart these two graphs are. So how do you do this? Well, what is the area of one of the triangles? So the area of one of the triangles is, area of a triangle, 1/2 base times height, but let's write it super pretty. This is going to be f of x minus g of x squared. You get that? Because it's the area of the square, but then it's, divided by 2. Or we can say also half the area of f minus g, top minus bottom. So same sentence here. How would we get the volume? We add them all up. Oops, sorry. Okay. The integral from a to b, wherever it starts and wherever it ends, you know that can be an intersection point, or that can be like a left boundary and a right boundary. And we're going to have 1/2. You decide, you can put that 1/2 in front, or you can leave it here, top minus bottom. How are you doing? Sometimes teachers run out of time to teach this and skip it because they think it's too hard because it's a bunch of different shapes. I almost think it's easier than the volume of rotation because a square is pretty easy. And then even on the AP, y'all, they kind of tend to give you an easier shape like these. But dun 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 dun, there's a harder shape. Okay, so this is a harder shape. This is the equilateral triangle, because there's some geometry in here that you either forgot or you never learned in the first place. Okay, so the area of an equilateral triangle isn't as easy as that other one there. Let's do this. Okay, so to find this area, we need 1/2 base times height, but we don't know the height, we just know the base. So to use, oh yeah, question. First of all, does this look like an equilateral triangle? No, but we're going to pretend it is. Sorry, I'm going very fast. What are all the angles in an equilateral triangle? We should know that. We should know that this is 60, okay? Which means this little angle here is 30. Now, a long time ago in a galaxy far, far away, you learned something called special right triangles. And a special right triangle, a 30, 60, 90, has a formula that goes like this. Next to the 60 degrees is x, the hypotenuse is 2x, and the next to the 30 degrees would be x square root 3. Remember that? Nod your head. Okay, now back to this. Our entire base is f minus g. So what would this little x distance be? This little x distance from here to here only, if I were to highlight it, I would totally mess up my highlighter with green ink. Hold on. I was blowing on it, so it would dry. I got these new pens, but they smear. What's the point? Okay, this piece here, you ready for this? This is half of f minus g. So this is called our short leg. Our short leg is half f minus g, which would mean the long leg is half f minus g times the square root of 3. Another color here. So this height, see what I mean? Do you see where this is going? Nope. Square root 3 over 2 of top minus bottom. If you're like, how am I supposed to know that? Well, I could say that's why you went to geometry, but most people don't know this, okay? It's hard. This one's hard. So the area of this entire triangle, so the area of one of the equilateral triangles, you ready? 1/2 base. What's our entire base? Is f minus g. 1/2 base times height. And then the height, Shoot, I tried to make this look pretty and now it's not. I ran out of room. Okay, the height here, you ready? Square root of 3 over 2 times f minus g. I'm still here. Are you still here? Let's clean this up. Oh my gosh. Okay. 1/2 times square root 3 over 2 would be square root 3 over 4. F minus g times f minus g is f minus g squared. So if you like, I don't think I've ever had a kid do this, but if you want to, you could memorize that. Yeah? And what shape is this? This is only for the equilateral triangle. So the volume would be, if we add them all up, top minus bottom, f minus g means top minus bottom. You know the calculus weighted, oh, I think on the quiz. Yeah, on the quiz, did you put dx? I just want to make sure I did it. Everywhere we go, people want to know what is f and what is g. F of x is greater than g, so that means top minus bottom. Top, and that's on the bottom. All right, last one. Half circle, semicircle. This one's neat, huh? I have some examples to show you in class, real life examples, okay? So that would kind of be a curved, whereas this is a sharp. Here we go. What's the area of one circle? So the area of a circle, let's see here, the area of a whole circle is pi r squared, which means the area of a half circle or a semicircle would be half pi r squared, but we need the radius. We don't have the radius right now. We have the diameter, right? Top minus bottom. The full oops, went too far. Top minus bottom. Okay, so if f minus g is all the way across, well, how do you find half of it? Like that. That's it? Yep, that's it. Okay, but be careful here, because this is going to be f minus g. The entire radius needs to be squared, so this is over 2, but do you see how this 2 is being squared? 1/2 pi r squared. All right, here we go. 1/2 pi. Let's square this 2. So this is going to be f minus g squared over what number? What is 2 squared? 4. And clean it up one more time. Okay, we're going to have, instead of 1/2 pi, let's write pi over, not 2, let's do 2 times 4 is 8. So that's the area of one of the semicircles. So how do we find the area, or the total volume? Would be, we take one of the semicircles, multiply it by dx, and then add them all up. dx, like that. Add them all up. Okay, that's the end of the notes. There's one more shape that is fun. It's a rectangle, but it's different every time. And it says a rectangle with a height that's equal to 3 times the width. So what that means is that you have your f over g, and so your base is f minus g, but then the height will be 3 times that. So the area of one rectangle will be, watch, f minus g times 3 times f minus g, because the height is 3 times the width. So height times width times height would be the area of one rectangle. And so the volume would be the integral of 3 times f minus g squared. Now, this is going to change every time, you guys. It could say the height is twice the width, or the height is half the width. So that number 3 is going to be different. That's why the rectangles although easy, different. Thanks for watching.